Okay, so we are very happy to have Biswajit from EPFL, who is going to tell us about a systematic approach to understand all orders of theorems and tail memory. So, Biswajit, take it over.
Okay. So first of all, let me thank you for inviting me to give a talk. So, and I'm apologizing for like not giving a presentation writing in my iPad because I'm still not comfortable with it. So I just made a presentation. And yeah, and another thing is that like the title of my talk is like too much optimistic, though we have not reached that goal, but I will try to tell that systematically how we can approach this goal and how much we have made success to it. So yeah, and I think like Prahad has given like very nice talk to how to measure gravitational memory, so that will be helpful to understand my work. So let me start by giving the outline, which I am going to tell. So maybe I should stop. Okay. So the outline of my talk is basically I will talk about first soft theorem in space-time dimension greater than 4. Then I will talk about soft theorem in space-time dimension 4. Then I will talk about how to take classical limit of soft theorem, and then I will talk about like from this classical limit one can extract the gravitational waveform, and then I will explicitly derive independently how to derive this long wavelength gravitational waveform, and I will show how it matches with the classical limit. Then I will talk about what are the implications of these derivations and like in terms of gravitational tail memory. So I should also tell that like all these results which I am going to tell, there is always electromagnetic counterpart in terms of soft photon theorem or electromagnetic waveform, but I will not talk about that thing today, though the electromagnetic part is better understood. And like the theme of the workshop is like just to mention, I think Prahar has already mentioned that where we can measure this gravitational memory. Like for example, if we consider like black hole merger problem, we know that when they are far apart and in spiraling, there we usually use post-Newtonian analysis to get the waveform. And then like when they are very close to each other in the merger phase, then one have to use numerical relativity because of the strong gravitational force. And then after that, when they form a single black hole, so then like to understand the ring down phase, one uses black hole perturbation theory. And then when all the ring down phases happen, quasi-normal modes died out. After that, if we wait for a long time, then we can measure the soft theorem. So soft theorem only helps to understand the gravitational waveform in this phase in the gravitational waveform diagram. So after some time, so in the late time, only we can use soft theorem to understand the gravitational memory. So let me, okay, so I will basically talk on mostly on these papers. So which I worked with Ashok Sen, Arnab Priya Saha, and currently I'm also working on one problem of determining spin-dependent tail memory, which will appear with Devadinno Ghosh. So let me start with telling soft graviton theorem in space-time dimension greater than 4. So what is soft theorem? So basically consider an amplitude which has arbitrary number of external finite energy particles which can have arbitrary mass and can have arbitrary spin, which we will call to be hard particles. And also this amplitude contains some small energy gravitons, which we will call soft gravitons. Then we start with this amplitude, and then we try to relate this amplitude with the amplitude which does not contain any of these soft gravitons. And the relation is basically via expansion in power of soft momenta. Soft momenta is the momentum of the soft gravitons. Like for example, if we consider for the single soft graviton case, suppose consider scattering where n number of hard particles are involved and one soft graviton with polarization epsilon, momenta k, and the hard particles have momenta pa and spin sigma a, then we can see that this n plus 1 point amplitude we can relate to a n point amplitude in terms of some operator operating on this n point amplitude. So like I have written down these terms as S0, S1, S2 as a power series expansion in omega, where this S0 goes like 1 over the energy of the subgraviton, S1 is energy to the power 0, order 1 quantity, and S2 is order omega, and possibly also higher order expansions. So I'll just explain that these results or this expansion, power series expansion since omega is true in d equal to 4 only at tree level, and for d greater than 4 those are valid for all loop orders. So let me proceed how one can derive these soft factors. So there are many prescriptions, but the prescriptions which I am going to explain is developed by Ashok Sen, which is called the covariantization prescription. So suppose consider the theory is described by a general coordinate invariant one particle irreducible effective action, and since it is a 1 pi action, so just tree level amplitude computed from this action gives the full loop amplitude result. So in a sense, like if we want to compute gamma n plus 1, then we have to compute such kind of a diagram where n number of finite energy legs are there and one soft graviton is attached with momenta k. And this amplitude we can divide into a subset of two diagrams. In one kind of diagrams where basically this soft graviton it attached to finite energy leg in the external leg, like in the external line. In a sense, like there we will have a propagator with momenta pa plus k. And the other set of diagrams where basically this soft graviton is not attached to any external legs, that set of diagram we consider as gamma tilde n plus 1. And then basically what we have to do, we have to find out what is this 3-point vertex gamma 3 and what is this gamma tilde. And that can be shown that up to some order in expansion of omega can be derived just by covariantizing the one particle irreducible effective action in the subgraviton background. But for that one have to assume that this gamma 3 and gamma tilde should not contain any power of soft momenta in the denominator. In a sense 1 over omega, those cannot contribute. In a sense this is also we assumed for a local quantum field theory, but this may not be true for a general one particle irreducible effective action. And if we assume this thing, then we can see from the first kind of diagram, since there is a propagator 1 over pa plus k with momentum 1 over pa plus k, so by on cell condition that contributes 1 over pa dot k. So this is 1 over omega. So this first kind of diagrams can contribute from the leading order like the S0 1 over omega, but the second kind of diagrams only can contribute at omega to the power 0. So like with this understanding, we can see that the assumptions which we made that the vertices gamma 3 or gamma tilde kind of amputated Green's function cannot contribute at 1 over omega, this is actually not true in 4 space-time dimensions. And that can be seen just from this simple example, like consider say 4 scalars phi 4 theory coupled to gravity, and then one graviton when running in the loop with momenta L. You can see when the loop momentum is in order of the external graviton with momenta K, it turns out that this kind of 5-point amplitude or 5-point amputated Green's function can contribute 1 over K. So this assumption is not valid in d equal to 4. That is why this prescription cannot be generalized to d equal to 4 for loop amplitudes. So now with this prescription one finds the soft graviton theorem up to subleading order. So I am just giving here the results. So this is this gamma n plus 1 point amplitude which is related to this gamma n amplitude if we just stripped out the polarization of the hard particles. So you can identify the first factor is basically the leading soft factor, which is determined in terms of the momentum of the incoming and outgoing hard particles and the information of the soft graviton, that is basically polarization and its momenta. Similarly, the subleading soft factor, which is basically you can see this is like given in terms of the total angular momenta of the hard particles, which involves the spin of the external particles as well. Similarly, if one try to analyze this thing up to subleading order, it turns out that in the subleading order there is a universal piece, but with this one non-universal piece, which means this is theory dependent piece appears. And this is very easy to understand. Like what happens is that for like you can couple the or you can, when you covariantize this action of the finite energy particles in the subgraviton background, since Riemann tensor is gauge invariant, so you can always couple Riemann tensor in an arbitrary way to the finite energy particles. And since the Riemann tensor involves two derivatives over the metric, so that gives it extra 2 power of soft momenta. That's why corresponding to leading soft theorem, it appears at subleading order, and this is like theory dependent piece. And like if one try to analyze that, okay, like how up to how much order we can do this soft expansion, like one hits problem at subcube leading order, and it is not quite known that for a generic theory of quantum gravity whether we can whether we can even show that thus like this gamma n plus 1 can be factorizable at fully factorizable at order omega square, which is the subcube leading order.
Biswajit, there's a question.
Sure.
And you have it.
Yeah, but that term that on the third line, it's not like completely arbitrary, right? There's some finite number of numbers, finite number of operators that can correct this term.
Right. So it has actually only two kind of things here contribution can appear. Once you fix the non-minimal coupling with the Riemann tensor, that is one kind of term can contribute to this order, and another kind of term contribute is basically the 3-point function which I showed, the gamma 3, which is basically two finite energy particles and one soft graviton is attached. So if you just give these two informations, then this term is completely fixed. No arbitrariness is there beyond that.
And then beyond that, we don't really understand how much ambiguity there is, because
yeah.
Prahar also has a question.
And isn't it also true that, despite the fact that it looks like this structure is depends on the type of terms they appear in the Lagrangian, actually the kinematic form of this extra term in fact completely is universal. The only thing you have freedom to change is just the coupling constant. The coefficient.
I agree. Like you can see this term is like written as R mu nu. So I have not explained, it is written as like R mu rho nu sigma, and this is basically the Fourier transform of the Riemann tensor, which is like in terms of epsilon mu nu and k rho k sigma, you can write it down. And like, so this structure is completely fixed, that only like Riemann tensor component R mu nu rho sigma in like Fourier transform, and that coupled to a factor n mu nu rho sigma. And also you can write this n in terms of the given non-minimal coupling in the theory at this order, and also contributions of this like 3-point function which is gamma 3, which I have.
So this n mu nu rho sigma, is that a fixed kinematic form? That
it has a fixed kinematic form. It is like, so it is like epsilon mu nu k rho k sigma, and then use the like antisymmetry and symmetry properties of this Riemann tensor to fix the other components.
Okay. Thank you.
Yeah, possibly I should write it down anyway.
Sorry, are you saying there's only one tensor structure that's allowed there and there's only one constant, or there are a couple of?
Okay, so only one tensor structure is allowed there, but there are two kind of possible coupling constant could be there. One is from the non-minimal coupling, and another is how this gamma 3 looks like in the two derivative order, the vertex. So only these two free parameters are there, but both the parameters contributes to the same structure R mu rho nu sigma. Yeah, I think this is like this is derived by Alok and Ashok Sen in their paper, the full structure. Okay, so let me proceed. So like now the question could be, okay, like fine, for a generic theory where non-minimal couplings are there, the matter particles can have arbitrary spin, it may be very complicated to extend this soft factorization to higher orders. But can we consider a very simple theory, say a scalar coupled to gravity minimally? And can we extend this factorization procedure there? So people have tried, like there are two papers from 2018 where they tried that, okay, let us use just gauge invariance, and using gauge invariance for this theory, at least at tree level, can we show that this factorization can be completely determined to arbitrary order? And like, let me draw again the same diagrams, but now just I removed this 1 pi vertex by just a minimal coupling, like graviton minimally coupled to scalar, and since they are spinless, so good. So then, okay, let's try to write it down that, okay, say gamma n plus 1 can be written as, like, since we know it is minimally coupled, so we know what will be the vertex completely. So we know that it will contribute like pa mu pa nu upon pa dot k. And then we know that like this scalar is entering to this endpoint function with momenta pa plus k. So now this is endpoint function, but one of the momenta is pa plus k. And rest of this gamma tilde n plus 1 we don't know, so this is an unknown function. But now suppose we assume that like the Taylor series expansion holds, and we try to expand in power of omega, which is valid in d greater than 4, but and d equal to 4 it is tree level true, so just expand it, and just we expand it in power of k, and just write it down in terms of unknown coefficient here, which coming from this gamma tilde, like calling r, and then from this I know what will be the coefficient, because this is just the derivative operating on this same gamma, and just expand it in a Taylor series. Now demand that, okay, this amplitude is gauge invariant, that is stripped of epsilon mu nu and like contact with k mu and k nu, and demand that this gamma n plus 1 vanishes. What you will find if you do that, you will recover exactly the up to subleading order all the terms just from the gauge invariance. Like you will recover this first term is 0 in the S1, since there is no spin, so you will recover this orbital angular momentum operating on this gamma part, and here also without this spin, this 2 orbital momenta operating on this gamma part, and there is no non-minimal coupling other thing, so this is 0. So that you can recover up to subleading order just demanding gauge invariance and using the structure that which I just mentioned, that two kind of diagrams with this kind of structure. So gauge invariance is enough to fix up to subleading order for this simple theory. But okay, we are not going to stop at subleading order. Can we extend this to sub to the power n order for n greater or equal to 3? If we try to do that, and just by gauge invariance, we find that a part of it can be completely fixed, which is I have written here, which you can identify is basically subleading soft factor, and then like k alpha del del pa alpha whole to the power n minus 2 number of this factor, and you can identify this factor easily because this will come just from the power series expansion of this gamma n. And the problem is that this part is gauge invariant fully, so you cannot, like, now you can add to this term with any kind of term which is like self gauge invariant, and this term cannot be fixed. Even it is not clear whether this can be written in terms of gamma n, that is in a fully factorized form, but you can just fix what will be the properties of this r, and that just from demanding gauge invariance, and that will be just if you like make transform mu and any of the alphas, or nu and any of the alpha, if you just exchange them, then it will have to be antisymmetric just to make the gamma n plus 1 gauge invariant, but you cannot fix this r completely. So this is the status of like the soft theorem at tree level in d equal to 4 or d greater than 4 loop level up to now. So up to now, is there any question?
Yeah,
go to the next section.
Andy has a question.
Yes, sure.
Can we understand the part that is fixed as somehow the higher angular momentum components, or how do we characterize which part of the say the n greater than equals 3 expansion, which part is fixed and which isn't?
Oh, the n greater or equal to 3, the first line is fixed completely, and this r term in the second line. So this part.
Yeah, I understand that first part is fixed, but what distinguishes it from the second line? Is that
okay? I
somehow higher angular momentum, or no? I know how it came out of the calculation, but how do I just say which part of the amplitude is determined by the soft theorem at order omega squared? Or order, what is this? Yeah.
Omega cube, starting from
omega cubed, yeah.
Oh, sorry, starting from order omega square. Yeah. So what happens is that this kind of contribution appears when the graviton is not connected to any external line, like it is connected to some internal leg in the tree level diagram. Like if you compute just for a simple theory, say phi cube theory coupled to gravity, and you can show that, like, suppose the graviton is connected to the propagator part. then you can show that like it is not always possible to like find out this factor R like in terms of gamma n, like factorizable. So yeah, so this is like from the S matrix perspective how it happens. Only I can tell.
May I ask a question too?
Sure.
I cannot raise my hand. I mean, usually the soft theorems are formulated in terms of the full amplitude and not of the, irreducible gamma.
Right.
Is the passage straightforward from one to the other? Okay, it looks that you get also some extra emission from the internal line, right? Because
right.
Yeah. So how does it go? Is it straightforward to go from gamma to the amplitude? That's the question.
Means starting from gamma n to gamma n plus 1?
No. I mean, gamma is one particle irreducible, right?
Right.
And you use that, I think.
Okay. Yeah.
The full amplitude is constructed out of gamma from 3 diagrams, right?
Right.
So which have internal propagators. And it seems that your recipe includes emission from those internal propagators.
Right. So
they should cancel out somehow. Because in the total amplitude, you only attach to the external lines, not to internal propagators.
No, like when there is some soft graviton is emitting, like it can, suppose you consider a phi cube theory, right? Where you have, and there is another propagator for phi propagator. And suppose in the internal, internal scalar propagator, one graviton is emitting from there. So that diagram, if you compute, you can show that so at the subleading order, so let me identify it. So this term, you can see you will get this term just from this contribution when it is connected to the internal line of the subleading order.
So it all works.
Yeah, so first term you will get when it is connected to the external leg, but the second term of the angular momentum you will get when it is connected to the internal leg. So you have to insert this soft graviton in all possible ways in the diagrams, and then only you will find the full factorization.
Okay, but the leading term cancels out, because I mean, what is internal for the amplitude is external for gamma. That was my point.
Okay, I am talking about like this 1 pi effective action, and then the diagrams are amputated Green's function. Like we already make this external lines to be on cell.
Let me make a trivial example. You have your phi cube theory and you have a 2-to-2 scattering process.
Right.
Where you exchange one quantum, okay?
Right.
A diagram. Now you telling me I take gamma. Gamma is a 3-point function. Okay, and to make it, to add the soft graviton, you attach your graviton to each one of these 3 legs.
Right.
Now you sew it back, you put it back in the amplitude. You end up with this graviton, which can be emitted from the internal line. Right. So that contribution should cancel in the leading 1 over omega.
Sorry, I'm
okay.
Yeah, I'm not being able to understand, but if the graviton is inserted in the internal leg, that cannot contribute at 1 over omega, right?
Exactly, but it seems to do so at the gamma, at the level of your gamma. That is my puzzle. I agree with the final result, and I was wondering if you can see easily. You see, when you have your gamma, you have 2 3-point functions, right?
Can you see who is gamma, gamma 3 or gamma n?
Gamma, okay. I was making an example in which gamma n happens to be gamma 3 also.
Okay.
And as you see in your diagram, you have You have a gamma 3 times another gamma 3, right?
Right.
Okay, now you construct the 4-point function out of two gamma 3s.
Right.
Right? That's the recipe to go from gamma to the amplitude.
Right.
Some 3s. And now you end up with a diagram for the 4-point function in which the graviton is emitted from an internal leg.
Right.
So apparently this is a leading term in 1 over omega, but it cannot be there. That was my question. But okay, I don't want to take too much of your time. We can discuss it on Slack if you want.
Okay. So means I'm possibly not able to follow like the diagrams what you are telling. Okay.
Yeah, one has to draw the diagrams and I cannot do it here.
Okay, sorry.
Sorry, go ahead.
Okay.
But I mean, if you look at the two papers that you mentioned, Amada and the other one,
Right.
they do exactly that starting from the amplitude.
From the amplitude, not
Yes.
from gamma.
Exactly.
Right. Oh, so yeah, so they started from the amplitude. This is like in our language, which I described earlier. I was just in this language, I just tried to like explore in this language, but yeah, I agree. Yeah.
Yeah, I mean, usually I always saw it done, as Paolo says, with amplitudes, not with gamma, but maybe there are some interesting advantages on using, the one particle irreducible action. Although I see this little problem, but probably can be, we can ask Ashok. By the way, Ashok had another meeting today, so he can only be there starting tomorrow. So too bad he's not there. We can ask him tomorrow.
Okay, sure.
I'm not sure if you can do from the gamma, because nobody has done for the dilaton. The dilaton can be done in the other case. In this, nobody has done the dilaton with the gamma.
Okay. So like for a moment, you can think this is like done for only tree level amplitudes. Like this is like, at least I want to mean that so I just tried to boldly generalize for gamma, but like for tree level amplitudes, like these are the results are derived for the minimally coupled scalar theory. Okay, so maybe, yeah, okay. I just tried to generalize the earlier idea. Okay. Now like, so this is the status in d greater than 4. Now can we do the similar thing, try to derive soft theorem in d equal to 4? So that in d equal to 4, the main problem is that the S matrix is infrared divergent, and this is the main problem. Then how to, like, if it is divergent quantity, then can we relate to divergent quantity, or how to derive soft theorem, or whether those really make sense because to relating to infinities. But the thing is that since soft theorem is a relation between two S matrices, and if we can show that like both the S matrices contain same IR divergent factor, like both gamma n plus 1 and gamma n, then possibly just taking the ratio or cancelling the same divergent factor in the soft theorem relation from both sides in terms of the IR finite part of the amplitude, we still can make sense of soft theorem. And this is what I am going to tell. And so what we are going to do is basically we start with a n plus 1 point amplitude, and we will try to exponentiate the full IR divergent piece from this amplitude and try to write in terms of some IR finite part of this amplitude, which we will denote by gamma n plus 1 g, and this g will be clear later. And then also try to exponentiate the IR divergent piece from the gamma n amplitude and in terms of the IR finite piece. And this can be done, at least this can be done, which I am going to tell, but at least in the when the loop momentum are smaller than the finite energy particles momentum in the IR limit. But what happens is that for electrodynamics case, both gamma n plus 1 and gamma n contain same IR divergent piece, so it is very easy to show. But for the gravitational case, when we are trying to derive soft graviton theorem, it turns out that gamma n plus 1 contains extra IR divergent piece relative to gamma n, and this is very easy to understand. what happens is this when the virtual loop when the virtual graviton is connected to a finite energy particles and the soft gravitons, that also contributes to an extra IR divergent piece which is not present in gamma n. So so we have to IR regulate this extra k phase factor, which I'm calling k phase, and the kgr is the known this iconal factor when in the IR limit. And then we can cancel from both sides of gamma n plus 1 and gamma n this e to the power kgr and try to relate what will be the what is the relation between this n plus 1 point finite piece of the amplitude and n point finite piece of the amplitude. And then we can try to find out what will be the soft factor S0, S1, S2, all those terms. So this is what I'm going to tell. So what we so basically what we have to do, we have to first factor out the IR divergent piece from the IR finite piece. And that thing, like for quantum electrodynamics case, actually is developed by Grammer and Ieni in 1973. And we basically generalized this idea for the case of gravity, and which I'm going to explain.
Can I ask a question?
Sure.
Can you just go back? I just wanted, so when you say it's k phase, do you mean that k is imaginary, or is it just e to the minus something that's
e to the minus infinity? K phase, I just name it phase because in the gravitational memory, I will show that this is related to some phase part. So that's why I just named it. But you can think this k is basically nothing but the same iconal factor. The kgr is the iconal factor when the virtual graviton is running between two finite energy particles, and k phase is the iconal factor when the graviton is running between a hard particle and the soft graviton.
But this k phase contains a real part and an imaginary part, right?
Right. It contains both real and imaginary piece.
I see, and you're dealing with that part as well, the imaginary.
Yeah, I'm dealing with here in the S matrix both real and imaginary piece. And I will show that what happens in the classical limit, in the classical soft factor, only the imaginary piece remains, and that's why I am calling this thing for a moment phase.
Okay.
Yeah. But this is just a nomenclature, but yeah, the meaning is possibly clear.
Sorry, can I ask you also one question? I mean, so basically what you're describing is that the IR divergences of gravitational amplitudes to all loop orders are just given by the exponentiation of the one loop amplitude, or the. So there's actually some ambiguity of what you're exponentiating. You can choose to either exponentiate just the IR divergent piece of the one loop amplitude, but you can also choose to exponentiate some finite parts as well.
Exactly.
So what scheme are you using to define your gamma G?
This is exactly I'm going to explain next. Like always, I can put some IR finite piece to the IR divergent piece, and I can exponentiate. So what I am telling here is that if you take the IR limit, then at least this k phase and kgr piece should contain the IR divergent piece, but it can contain more. So I'm going to explain the prescription, how to do this. So the strategy is that what we will do is that we will split the full graviton propagator with momenta say L, which is flowing from particle A to particle B. And we will split this into two parts, and one part we will call K graviton, and the other part we will call G graviton. And this is, you can see the propagator for the graviton in Didonder gauge, and we are splitting this just K in terms of two terms. One is K and another is G. And how to choose this K and G? So first one is that the demand is that if we compute any loop diagram with the K graviton, which is the K graviton propagator, then that should contain the full IR divergent piece, but it can contain something more also, but at least it should contain the full IR divergent piece. And if we compute a one loop diagram with the G graviton, so that means this is completely IR finite. And this is one of the demand. And with this also, I like to how much this K contains extra piece. To fix that, I will demand that if we compute a one loop diagram with no external soft graviton, or no external graviton is there, only finite energy particles, say for scalar theory, only scalar particles are there, no gravitons, for this one loop diagram with G graviton propagator will completely vanish. So in that way, I can put some IR finite piece also with this IR divergent piece in the definition of K. This is how I will show you what is this k and g in the next page. And the another thing is that, so that this word identity kind of relation valid, so that we make this virtual k graviton to be choose to be such that it will be like a pure gauge kind of thing. So it will be like proportional to L momentum of this graviton, such that if we insert this graviton to a scalar line, we can write it in terms of two diagrams where this k graviton is connected to extreme left and extreme right. With this, we also can check that if we choose properly this k, we can also check that even this, like even if there is a external graviton is there, if we just choose this k such that it goes to the extreme left of this k, extreme right of this k, and connected via this like two scalar two graviton vertex, then this diagram vanishes. So this will help to even, like if we insert a k graviton, it will help to propagate to the for the diagram to the extreme left and the extreme right. So if we demand all these conditions, we can construct what will be this k and g, and this is the result of the construction I have written here. So this k basically looks like, you can see this is proportional to L mu, L nu kind of factor, L rho, L sigma, which will help to do the first process. When we insert a k graviton, it will split into two parts. And the other thing is that we choose this C in such a way such that it contains the full IR divergent piece, and also for demanding, also demanding the fact that if we compute a one loop diagram with G graviton, it vanishes. We can completely fix all the terms in that way, and we can show that at least at one loop order we can write the amplitude in terms of this in terms of a IR divergent factor, which can contain also some IR finite piece times a completely IR finite amplitude. So this is the construction I have given, but just let me give a disclaimer that this full exponentiation of this iconal factor analyzing all loop orders has not yet been proved with this construction, which is there for QED case. Like this KG decomposition, the original paper has shown that for like electromagnetism case, like it is possible to show the exponential analyzing all loop orders. But for gravity, since this multiple self-graviton interaction could be there, so it is little harder to prove it. So this is not yet done. But since we have done analysis only at up to one loop order, so up to one loop order, we have checked that this helps to factor out the IR divergent piece from the IR finite piece. And so, and this will be enough to derive the subleading Subgraviton theorem, which I am going to describe. And now it happens that at subleading order, the soft factor is not omega to the power 0 like d greater than 4, but it goes like log omega in small omega expansion. So what we have to do, so now what we have done is that, okay, so in the loop graviton, we split it into two parts, k graviton and g graviton, and the k graviton is the IR divergent piece, so cancels from both sides. So in the first kind of diagrams, this is the one loop diagrams, and k is the like this is the basically the external graviton with momenta k. And now this kind of diagrams only we have to evaluate with the external, with the loop, with the virtual graviton, which is the G graviton. And then the rest kind of diagrams where this splitting of this kg has not been done because that contains some extra IR divergent piece which is not there in gamma n. So that part we have to evaluate with the full G graviton propagator. And if we do this thing and try to and put a IR cutoff for this kind of diagram, since this contains the extra IR divergent factor, and try to analyze, we can see that now these diagrams can contribute to log omega when the loop momenta is greater than the momentum of the external gravitons. In that range, if we approximate, we can find that it goes like log omega, or it contributes to log omega. And this kind of diagrams contributes to that region also, but with a region when the loop momentum is smaller than omega and greater than the IR cutoff, there also it contributes to log omega, and that basically gives this phase contribution which I was telling. And so let me show the results, and I can explain from where it come from. So it happens, so at subleading order, we find that it goes like log omega, and the coefficient of log omega I have written here explicitly. So here you can see that those are determinants in terms of the momenta of the incoming and outgoing particles, and the momenta and polarization of this subgraviton. And one thing I want to mention, the first two lines, so I am using the convention eta A is +1 if the particle is outgoing, -1 is incoming. So in the So you can see this log omega coefficient has a double sum over the particles, not like the tree level diagrams where only the single sum. So there is a pair of sum of particles, and the first two kind of terms is, you can see there is a constraint over the sum over AB particles where eta A eta B equal to 1, which is basically these are non-vanishing, only both the particles are outgoing or both the particles are incoming. On the other hand, the last two kind of terms, there is no constraint of incoming or outgoing. So this basically, even if A particle is incoming and B particle is outgoing, still these terms are non-vanishing. And this is the full log omega contribution. And now I'm going to tell like I can write down this result in a different way, and this gives a very good observational point.
Usually there is a question, Andy has a
Sure.
question.
Yeah, where's the, I'm sorry, I'm not seeing where, is log omega? I don't see a log, where's log omega on the first?
Sorry, I just have written the coefficient of log omega term. So in each term there is a log omega. So this is the coefficient of the log omega.
Oh, so this is all multiplied by log omega.
Yeah.
And is this all vanish if there are no massive particles, no stable massive particles?
Even if for massless particles, these are non-vanishing. If all the particles are massless, still this log omega is present.
Sorry, if they're all massless, it's still there?
Yeah, if all the hard particles are massless, still this is non-vanishing. For electromagnetism, it vanishes, but for gravity, like even if they are massless, still it is there.
I see. And the way you described it sounded like it had to do with infrared divergences, but I don't see an infrared cutoff in here. Is it log omega?
Yeah, so let me explain. Like what happens is that, so this kind of term, the second line and the fourth line,
yeah,
these are basically coming from these two kind of diagrams when the loop momentum is smaller than omega and greater than the IR cutoff. So this, the log appears in the second and fourth line. These are basically not log omega, but log of omega r, if you call this r to be the length of the IR cutoff.
Okay, so if you use some kind of coherent state formalism, which would be relevant to a classical scattering problem in which the infrared divergences are all absent, would this effect still be there?
Yeah, still be there. Yeah, like I'm going to tell, like if we just write.
You could have derived it without ever mentioning infrared divergences.
Yeah, like what I am telling is that, so this R is, like you can see, like suppose some gravitational radiation process is happening. So what can happen is that if you put a detector at distance R, you really cannot measure a wavelength which is greater than R because it will pass through the detector. So you have a natural cutoff for your process. And this basically gives you the IR cutoff.
No, if you wait a long time, you can still measure. I mean, that's like the memory effect, right?
Yeah, but if the omega or the lambda, which is basically the wavelength of the gravitational waveform, if this is greater than R is, you are not supposed sitting at infinity, at this infinite distance, but at a finite distance R, right? Then if you are sitting at a finite distance, obviously you can, like you cannot, if you sit at infinity, then in the gravitational waveform that contributes to 1 over R. So it will like, it like R0, what Prahar was telling, if you take strictly R0 going to infinity, it will vanish. But at a finite R0, if you sit, then you already have a natural cutoff for lambda, that lambda cannot be greater than R0. Otherwise, it like you cannot observe that waveform. And that is the IR cutoff, which physically tells you to put to regulate the IR divergence issue.
Thank you.
Thank you. So let me proceed. So what I'm going to tell is that this result you can write in a form from which like you can see that possibly even without doing all this analysis, you can expect this result could be derived. So this is this slide. So this sort factor which I have written there, this log omega term, now I am including the log omega factor also. This is I am calling the subleading sort factor. This can be written as a, whatever I was showing this k phase term, which was the iconal factor when the graviton is propagating from a finite energy particles to soft graviton. If you multiply this phase, if you evaluate this phase factor in a regulated range of integration, which is from IR cutoff to the energy of the soft graviton, and you multiply it to the leading soft factor, and similarly this is the tree-level subleading soft factor operating on a iconal factor, which is when the graviton is like propagating from two finite energy particles, but now regulated in a range when the loop momentum is greater than omega and less than the energy of the finite energy particles. Then also you can see the subleading soft factor can be just written in this way in terms of the tree-level soft factors. So what this is telling, like, so just what I want to mention is this KGR regulated is basically, you can see this is the iconal factor when the loop momentum is greater than omega, and this K phase is the same iconal factor, but the loop momentum is smaller than omega. So what this is suggesting, if you just naively assume that okay, tree-level soft theorem is valid even at loop level, or the d greater than 4 soft theorem is valid even in d equal to 4, and write down naively this amplitude. Now you see we have told that this gamma n plus 1 basically written as exponential of some k phase and exponential of kgr, and this gamma n is exponential of kgr, right? And now suppose you regulate this k phase kgr in the integration range which I mentioned, and just substitute in this expression and then commute through these tree level soft factors. Then you can see if you like this differential operator operating on this kgr regulated will receive a contribution, and this kgr regulated goes like log omega and this k phase goes like omega log omega, and you can see that since the gamma n plus 1 has this extra factor, if you just expand it, it will multiply to the 1 over omega piece and also can contribute to log omega, and this is exactly the factor which I have written in the earlier slide. That means, like, if we just consider the naive tree level soft factors are valid for the full amplitude, but with the fact that the integrals are now regulated in the specified region I mentioned, and then just you commute through this commute through these tree level soft factors, you still can recover the result which I mentioned here, and explicitly the expressions are written earlier. So this is just one observation which I wanted to mention, and what this observation is telling is that though we have derived this result at one loop order, but since this exponential, if the exponentialization is true, which is not yet proved rigorously, then this is like valid to all loop order. That is, this log omega correction will not receive any contribution from higher loop order, because the higher loop order contribution is just the one loop exponentiation of the KGR. So this is the point which I wanted to make for the d equal to 4 soft theorem. Now, like, if we suppose now we observe this thing and try to, okay, like if we don't evaluate the sub-subleading order, try to generalize this observation, and we can conjecture that what will be the sub-subleading soft factor will look like. And there, if we just generalize this idea and assume the sub-subleading soft graviton factor, which we know from higher dimensions or tree level in d equal to 4, and just generalize this idea of exponentializing this k phase and kgr, we can conjecture what will be this sub-subleading soft factor will look like. And it is, you can see this is the phase square times the leading soft factor, because phase term will go like omega log omega. So this is omega log omega square times 1 over omega. So it will like omega log omega square at the leading non-analytic order. And obviously there is a omega log omega correction which we cannot determine because of the fact that this log omega has a scale. Like log omega is not a dimensionless parameter. So like there is a scale of this omega, and this scale, like if you choose like 2 times r or 4 times r, that will give a that will correct this omega log omega contribution. So only we can fix omega log omega square contribution, which is the leading non-analytic piece, which you can derive analyzing 2 loop amplitudes, and like which we have now derived from the classical analysis, which we have proved the classical part of it, which I am going to describe in a minute. This is the conjecture, and which you can prove analyzing 2 loop amplitudes, which is not yet proved. So
I think Andy has, I'm not sure, his hand is raised.
Okay, so let me proceed then. So possibly then we can try to see that, okay, like can we do this even higher order, say sub to the power n leading order, and we can try to write it down. But since there are still this r factor which I shown earlier, even at tree level it's undetermined. So like without knowing this r, we cannot fully specify what will be the form, but from the rest of the terms we can conjecture how this structure will look like. And I'm not going to tell too much about it. Only what I can tell is the leading non-analytic piece from the n loop will turn out to be omega to the power n minus 1 times log omega to the power n factor. So this is just like extending our observation for the n loop case. So here I am giving a table like from which order how we will get contribution. So from tree level we have seen that the leading sub factor goes like 1 over omega, the subleading goes like omega to the power 0, subleading order omega, so you will have a Taylor series expansion in omega. From one loop the leading non-analytic piece turns out to be log omega, then you will have obviously omega to the power 0, and then omega log omega, omega square log omega, all these higher order terms. And just I want to mention this omega log omega term turns out to be spin dependent piece, because you know like how spin couple to finite energy particles, this is coupled via the spin connection term, and the spin connection term basically turns out to be derivative over the VL which is basically kind of metric component. So that contains an extra factor of omega soft momentum. That's why relative to the minimal coupling part or the momentum dependent part, the spin dependent term comes with a factor of omega. And also then you can analyze two loop, and it turns out to be leading non-analytic piece turns out to be omega log omega square, and then like there are other kind of terms which like cannot be fixed because of the like scale like which fixes the omega log of omega what. So you can also generalize to n loop, and you can predict the structure which I mentioned earlier, and the leading non-analytic piece we expect to be completely fixed and factorizable, and like it is expected to be universal, just like from the understanding which I mentioned earlier. So this is like too much optimistic viewpoint, like how much we can expect just observing what we have done. So this ends my like soft theorem derivation from S matrix.
So Biswajit, you have 6 minutes, but okay, I mean, I think there's also half an hour discussion, so you can take some of obviously that time. Just wanted to mention that.
Yes, sure. Thank you. So now like I'll discuss about the classical limit of soft theorem. So for that, I think this is already discussed in the last week by Ashok Sen. So let me just briefly discuss. So like say consider like start from d greater than 4, and what is classical limit means is that like only single soft graviton emitting, that you cannot take to be considered as a gravitational wave in the classical limit. Only if at a particular frequency range a large number of graviton, like large number of coherent state of gravitons emitted, and then you can consider this to be a gravity wave. So like for that you have to start with a multiple subgraviton theorem, and that also we have the result, and you take that. Okay, so for a multiple subgraviton theorem we take a limit that when large number of gravitons should emit, and that if you demand, it turns out that the scattered object have to have mass which is large in the unit of Planck mass. And also you want that the radiation frequency to be small, or the gravitational wave frequency to be small, so the total radiation energy you can assume that this is small like compared to the total total radiation energy has to be less than the energy of the finite energy particles. And this if you demand, then like you have to scatter in a large impact parameter regime or a probe scatter limit when one of the object is very heavy and like the probe particle is scattering in the background of that heavy object. But like this can be relaxed, and later it can be relaxed and one can still derive the soft theorem. So what this tells us, if we just assume these two conditions in the classical limit, then it will tell us that okay, you have to replace the orbital angular momentum operator by its classical angular momentum, and the spin operator to be by the classical spin of the object in the soft factors. And also you have to drop the contact terms which I have not shown in the multiple soft factor. And then like what happens is that if you do this and then independently compute from two, like independently, if you know h mu nu, which is the metric fluctuation, you can compute what will be the radiation energy. On the other hand, from the soft theorem, you know how the soft factorization happens. From there, you also compute the radiation energy of the graviton and compare these two things, and what you will get is basically the gravitational waveform. This E alpha beta is basically the trace reversed metric fluctuation and its Fourier transform in time variable. And if you contract with the polarization, it turns out to be completely proportional to the soft factor in the classical limit. That means you just replace operators, orbital momentum operators by the classical momentums and the spins by the classical spins. And like, which tells us this waveform is like proportional to the soft factors, and this is since it is derived from the energy, so there will be some phase ambiguity. So up to some phase this relation is correct, and also this normalization is fixed. So now, so here, like, I just want to tell for d equal to 4, if you try to specify this thing, this relation will look like this, that this is the Fourier transform in the time variable of the trace reverse metric fluctuation contracted with the polarization turns out to be this normalization with some undetermined phase psi times the soft factor, where the soft factor is written here, which is the lead. You can up to subleading order, I have just written it down. This is the leading soft factor, and this is the subleading soft factor, where this J rho sigma is not now the derivative of the momenta, but you have to replace the classical, which is the R cross P term for the orbital piece. And rest of the thing which I want to mention is that, like, so this E mu nu, like where the x vector, where we are detecting the gravitational waveform, that is at distance, that basically x vector, which is set up at distance r along the direction cosine denoted by n hat, and the momenta k mu is basically omega, which is the energy of the soft graviton, and which is this, and the n mu has the like zeroth component is 1 and the unit vector along the direction of the detector from the scattering center. So if we do this thing and try to see that how it will look like for d equal to 4, it turns out that in d equal to 4, the subleading soft factor diverges because of the fact that due to long range gravitational interaction, the trajectories are not like they are moving at straight line trajectory at infinity, but it receives a log sigma correction, where sigma is the proper time, and that means like it is not even at like large time, it is not moving at constant velocity, but it is accelerating. And this acceleration term one can determine just by solving geodesic equation. But more than that, what happens is that the classical angular momentum, which is like in terms of the trajectory of the particle, we just substitute here, it turns out to be goes like log sigma, which if you take strictly sigma going to infinity, it diverges. But from the physical ground, we know that if we want to determine the gravitational waveform with frequency omega, then after the time of the trajectory, which is sigma, in order of omega inverse, we cannot this cannot contribute to gravitational waveform with frequency omega. So there is a natural cutoff for this sigma, and this is like the omega inverse. And then if we just substitute this thing, then we can like find out what will be the soft factor. But before that, just I want to mention one observation. Here we can just solve the trajectory of the equation and find out the acceleration term, which is the coefficient of the log sigma in the trajectory. And what we see is that if we just replace log sigma with log omega inverse, then this I times c times log omega inverse turns out to be the momentum derivative of the same iconal factor, but when we evaluate the iconal factor not with the Feynman propagator but with the retarded propagator. Is there a question? I can see. Okay, so what I want to mention is that the acceleration term can be identified with a derivative with respect to the same iconal factor, but when the iconal factor is evaluated with the retarded propagator, not with the Feynman propagator. So what this tells us that, like, if we what this tells us that if we just now replace this Ca log omega inverse with respect to del del Pa mu of the same iconal factor, regulatory iconal factor, but with retarded propagator, we can get the gravitational waveform up to subleading order. And if also one have to take care of the backscattering effect, like due to the long range interaction of the gravitational long range interaction on the gravitational wave by the matter particles. And if you take care of all these things, we can show that this subleading order gravitational waveform, which goes like log omega in the frequency space, that has this kind of behavior. This is, you can identify the soft factors which I have written down. Only the difference is that this k has now a superscript CL, which is the classical, not the regulated piece, which means that we have to evaluate the same regulated phase factor or regulated KGR, but with a moment, but with the Feynman propagator replaced by the retarded propagator. So in that way, like, we can predict what will be the long range gravitational waveform just starting from the classical limit of the soft graviton theorem in d equal to 4. So
you are not done, right, Biswajit?
No, I am not done.
Okay.
Yeah, if there is any question, just I can try to answer. Okay. So one can then, like, again generalize this observation to predict the spin dependent part of the gravitational waveform starting from the subleading soft factor. And like here, just I have written it down, just like use the subleading soft factor which we have mentioned in d equal to 4, or we conjectured in d equal to 4, and just replaced all the regulator level by the classical level, and I just mentioned the meaning of this classical, and then expand in power of omega, and you can also extract the spin dependent gravitational like waveform, and it turns out to be at order omega log omega, like the which I also mentioned in the table, and this one can predict. But this is not fully this is not the full contribution, because like it will receive contribution from order g cube, which are not like, which is like telling that to determine the spin dependent gravitational waveform, like it is not just universal or completely determined at g square order, but it will receive correction from higher orders. But like, so you have to do both a post-Minkowskian expansion in power of g as well as in power of omega to get the like log omega, to get the spin dependent omega log omega piece. But the other cases which I mentioned, the log omega or the omega log omega whole square which appears at the leading non-analytic piece, those are completely determined at that order of g. You don't have to go to you don't, like, these are exact at that order of g, don't receive correction from higher g. G is the gravitational constant. So is there any question up to now?
So Biswajit, just to clarify, the omega log omega spin dependent piece is universal. Is that?
No, it's not universal. In a sense, you can see like only we can determine the order g square piece, but not order g cube piece.
Okay.
And order g cube piece also has contributions, because if there is omega log omega whole square, then this log omega scale can contribute to omega log omega. So this is not completely fixed. And also you can see like this depends on this RA, RB, which are basically in the orbital angular momentum. These are basically the impact parameters. So not only you have to give the data like of the incoming and outgoing momenta, but also the impact parameters.
Right. You said two loop, there is a omega log omega, so that's the non-universal contribution.
Yeah.
But at one loop, there's a universal contribution from the spin.
Yeah, at one loop, there is a universal contribution. Okay. Right. Yeah, now, so if there is no questions, okay.
Yeah, I'm looking at the participant. If there is any question, I'll tell you.
Okay, sure, thank you. Yes, okay. So now we can try to give a systematic, like up to now we just have taken classical limit of soft theorem and try to tell how the waveform look like, but we can independently, without going through S matrix, just from the classical like scattering problem, we can also derive the low frequency gravitational waveform, and we can check that whether our predictions from the soft limit of the S matrices are still true or not. And like for that, we consider kind of a scattering process where suppose m number of particles with momenta p1 prime to pm prime are coming in and goes through some complicated interactions, and then going n number of particles are going out. And suppose this complicated interaction is happening in some finite region of space of size L, and then what we want to determine is basically what will be the gravitational waveform with frequency omega, which is much smaller than L inverse. In a sense, the wavelength is greater than the length scale L. Or in like if we do a Fourier transform, we want to determine the late time or early time gravitational waveform with time u, which is much greater than this length scale L. So these two things are related by Fourier transform. So this is our goal, and the region R we will choose such that all the complicated strong forces or interactions are happening inside region R, and outside only long range gravitational force is present. And this can be choose like for a special case, like for say consider for a black hole merger problem, we can choose that after the time when the kinetic energy is greater than the potential energy, that sets up the scale, that is when then we can consider the interaction strength to be small, and that can set up the length scale L. So then what we have to do is basically we have to solve the Einstein's equation and the geodesic equation to iteratively to find out each order in G how the gravitational waveform will behave in small frequency limit. So for that, here just I defined the metric fluctuation h mu nu to be the deviation from the eta mu nu, and the trace reversed metric fluctuation here. And in Didonder case, this linearized Einstein's equation takes the following form, where in the right hand side this T mu nu has both matter part and also the gravitational energy momentum piece, which is basically just from the Einstein tensor if you just subtract the linearized piece. And then if you try to determine the time Fourier transform of this waveform in small omega limit, it turns out that this can be related to the full Fourier transform of the energy momentum tensor times 2g upon r. So the goal will be to determine then the Fourier transform of the energy momentum tensor in small omega expansion, and that will determine the E tilde mu nu. So due to time, I'm just skipping the details, and let me tell the strategy why this iterative expansion works. Because in c equal to 1 unit, it turns out that g m omega, m is some mass parameter, which is the momentum of the particles or the mass of the particles which are or objects which are scattering, and g sigma omega square, g m r omega square, all these are the dimensionless parameter. So it tells us that like expanding in power of g is a good parameter, because that can take care of the corresponding like m omega piece or the spin dependent piece and all these orders. But like we have to start with the energy momentum tensor, and we know that the energy momentum tensor has a like full derivative expansions up to subleading order, which is the spin dependent piece. It is like completely like fixed, but after that order, like the structure of the objects will come in terms of like the multiple moments and the tidal effects and other terms. So but those will be important, those will not be important to our analysis, because if we are interested to the few few leading non-analytic piece, since those involves more derivative over delta function in Fourier transform that contributes more power of momenta, so it will be subdominant. So up to the order which we are interested, we can just throw them out, and like we can just take these two terms and we can try to analyze. And similar thing happens for like gravitational energy momentum tensor also. You can add higher curvature terms, r to the power 4 r square, all these terms, but since they all again involves more derivative over metric, so that gives more power of omega, so it will contribute more subleading order in omega expansion. And so the strategy will be basically we have to solve the Einstein's equation to get corrected metric and geodesic equation to get corrected trajectory, and we have to do this iterative order in G. And finally, we have to compute the Fourier transform of the energy momentum tensor in omega going to 0 limit and try to extract the non-analytic pieces. And I am skipping the details and try to tell you, like if we try to derive, it exactly matches with the expectation which we just mentioned, like from the classical limit of the soft theorem. And here I am giving a like list. So this omega to the power -1 from like 0 loop, and this is iterative order G, it appears, that contributes to memory at heaviside theta function of u, which Prahar discussed, that you have to take the change of the metric fluctuation from u going to minus infinity, u going to plus infinity, and that difference will give the leading memory, which is known. And but like tree level, the starting from the subleading order, which are in power of omega only, those contributes to delta u, delta prime u, and all these things. So they are like only valued near u equal to 0. That those cannot contribute to the difference between the gravitational change of the gravitational wave from u equal to minus infinity and u equal to plus infinity. So those cannot contribute to any displacement kind of memory. But like there are some proposals of other kind of memory, not displacement kind. These terms could be important. Then like at one loop order, like it appears to be log omega, and that gives a 1 over u tail memory. And similarly, I'm just focusing on the leading non-analytic pieces. Then at 2 loop order, it goes like omega log omega square, and that contributes to a memory u to the power minus 2 log u. And an n loop order, which is go like g to the power n plus 1 in classical iterative expansion, and which contributes to u to the power minus n log u to the power n minus 1 memory. So you can see that there is like tail of tail memory. So like there will be lot of tail memory, and all of this will be like important if you are like not at strictly u going to infinity, but some finite u, and you have to choose this u such that the like all the strong interactions already happens, and only long range interaction is there. After that time you consider this u, and you can extract all these coefficients systematically. And so these are the explicit expressions of these terms, which I am skipping in the discussions. If someone asks, then I can only tell. And just I want to mention that what Prahar is telling, that whether this memory can be observable or not. So for some kind of observations, like for core collapse supernova, hypervelocity stars, neutron star merger, all these processes, taking data, we try to evaluate that what will be the change of the detector position with respect to the original position, which is known as the gravitational shear. That turns out to be in the order of 10 to the power minus 22, which is like in the age of the current like LIGO detector resolution. So in principle, like those could be observed. So we are hoping to observe. And also just want to mention this, all these tail effects which I am mentioning, like those are also in the same order, like 10 to the power minus 2, if you are not taking u to be too large. But what happens for a black hole merger process, when only the final state is one massive black hole and all are gravitational massless particles, all these u to the power minus 1, u to the power minus 2 log u terms vanishing, like because like you have only one massive object and all other massless particles. That can be observed just from the expression if we go to take this limit. And this is one of the prediction. This is vanishing of this gravitational tail memory will be a test of the general relativity. So let me thank you and finish here. I am over time, sorry for that.
Thanks Biswajit, for a very nice lecture. I think it's all thanks. We still have 15 minutes for discussion.
Well, I have a question. I should have raised hand. Concerning the vanishing of the u to the power minus 1 tail in the case of binary black hole merger, this is due to it takes into account the nonlinear memory. What is the proof that the coefficient of u minus 1 is 0?
Oh, like, okay, so let me so this is like the coefficient. So, and I want to mention that all these tail memories are all 1 over r order. Like in r expansion, which the distance from the center to detector is 1 over r. And so, and this 1 over u term, you can see like what happens is that there is two kind of contribution. One is this first line, which I was telling, the kind of phase term multiplied to the leading memory. So this is also, people have earlier explored this thing. This is this tail term is already known earlier, but with this, due to the long range interaction between the finite energy, the objects which you are scattering, this is the extra tail part is there. And what happens if we take the in the finite energy particle sum, if we consider one of the particle is a massive and all the rest are massless, which is true for black hole merger problem, then there turns out to be cancellation between this first term and the last two terms, and it vanishes. So this is just an observation. what is the physical understanding or why this is vanishing, that is still not clear to us.
But are you, if the scattering, there are two massive bodies coming in. If I send two massive black holes and they capture to merge,
right?
And then I have, in the exit, I have only one massive body and massless. Are you still saying the coefficient of 1/u vanishes in the tail?
Yes, yes, yes.
Even, okay, you are saying this.
Yeah, yeah.
Thank you.
Andy has a question.
Yeah, I suppose this is a question for Thibaut. You made some comment during the last talk that these tails had appeared previously from some other kind of analysis. That you had some other. Could you clarify for us what? I'm not sure I understood you correctly, but how is this related to? Yeah.
Okay, so you mean the 1/u tail here?
Yeah.
So, for instance, yes, actually you were in Cargès, no, at the time when Ashok first in 2018, no, presented this.
Yeah.
In our 1992 paper with Luc Blanchet, where we had analyzed in a PN sense the tail, including both actually the so-called memory and the memory tail. And then we had noticed, but without doing the exact thing in a PM sense, that the large U limit of the tail integral in the radiative, in the waveform, HIGATT, would be 1/u, would decay like 1/u.
So I guess in the recent work, there's some formula for the coefficient.
Yeah.
And
yeah, exact. And in post-Minkowskian, yeah, we had the multiple expansion and PN expanded, yes.
I see. Thank you.
There are a couple of other hands up. Prahar was first.
So I just want to confirm the scales that I'm looking at here. So would you say that these formulas are valid when R is much greater than U?
Yeah, R is like U is in between the length scale L and R. L I introduced is basically the scattering region where the strong interaction is happening.
Right. So these tail effects are really tiny because they're of second order, like roughly order 1/r squared, right? Because
no. So like this, you can choose this U to be much closer to L. Like what I am telling, how to choose this U. So you have to choose when the interaction strength is becoming weak. You don't have to take to be infinitely weak. Like so, and that means like when suppose between two. Consider one particle which is moving, it has some kinetic energy and it is feeling a long range force potential energy due to other particles. So when the kinetic energy of the particles is greater than the potential energy due to the long range force, just at that scale, from that time scale you can trust our formula, and that sets the value of the U. And if you try to determine with that U, then you can see that this tail term is same order to the leading gravitational memory.
So whatever you take, R definitely has to be larger than that.
Yeah, R has to be definitely larger than. So R is both the term has 1/r term. Yes. You see that this first line is the gravitational memory. This is gravitational DC memory. This is the tail memory. So both are 1/r. Now this 1/u, you have a set of, like you can see with respect to this term has a factor of g and a power of momenta in the numerator, which basically g times m upon u is the dimensionless quantity. So this term is the dimensionless quantity, and it turns out that this u, basically you can trust this formula when u is in order of g times m. So this term is order 1. That means leading and the tail term are in the same order. So both are like in the same order, and like these are not tiny with respect to the gravitational memory. But if you go to strictly you going to in the order of r, when u is in the order of r up to that large time, then obviously this is subdominant relative to the
I see.
leading memory.
And also just one question about the G Newton that's appearing here. That's the
Right.
renormalized G Newton. What's the renormalization?
Oh, this is okay. So
going on
this
with
is
G Newton?
completely a classical result. So this is just classical G Newton.
Oh,
what
I see.
the observation G Newton is.
Oh yeah, of course. This is the classical limit of the. So in the soft theorem, sorry. So then maybe I ask them in the soft theorems when you wrote down all of those formulas, those were all the renormalized G Newton at some scale. What is the? How should I make sense of those?
Okay, like I think I should consider this as like in the effective field theory language, like where this whatever like I started with the like say scalar coupled to gravity, so I can think these are valid in the energy range. Like okay, possibly.
Yes, it will be right, Biswajit. It will be renormalized. Yeah, in the effective field theory.
Yeah.
So this is the G at the UV scale. So now you need to have a UV scale and you need to have an IR scale. So the G that's appearing in your soft theorems, which scale are you evaluating that G Newton at?
Okay.
I think it's at 0.
At 0.
Yeah, at 0. Yeah.
At the IR.
Not the UV. I mean,
not UV.
Clearly, the low energy effective action of the theory.
Yes.
Yeah.
So strictly G Newton in that limit, G Newton should go to 0, right? Because in the IR, given the dimension of G.
No. Why?
No.
Why Newton goes to 0?
I don't know. It's a effectively dimension-full parameter with positive mass dimension, and
it is, but that's why I don't think it has the usual running of a gauge coupling. You know, you just can fix it at 0 momentum through an experiment.
Okay.
Through Newton's experiment.
Yeah. Okay.
Rodolfo has a question.
Yeah. No, just to make sure that I understand, wanted to go back to this question of the memory effects vanishing when you have just a single final state.
Right.
If instead you consider really a 2-to-2 scattering, in that case you do get an untrivial result.
Yes. Right. Like for what happens for neutron star merger case, like there are like finite, like in the final state, not a single particle but multiple, and for that case we determined the order is like gravitational memory is 10 to the power minus 22.
Yeah,
so it is not
actually I had in mind even a simpler kind of more Gedanken experiment, right? Instead of having kind of matter ejected away, just think about a unbound orbit, right? Really a scattering, right? And then suppose that it's super energetic, and so it creates enough gravitational wave that we can detect, right? And then in the final case, you have the 2 states. Just elastic.
So it is non-vanishing. Yeah.
It is non-vanishing.
Yes,
okay. Yeah. Thanks.
Yeah. It is non-vanishing.
So Biswajit, maybe I can just ask something. This is actually regarding what Andy also asked Thibu. So the initial, is it correct to say that the new results you guys have, the one important thing is that the initial and final moment are assumed to be, given independent.
Right.
And then you derive the universal terms in terms of initial and final momenta. And this is why the source multiple moments never really appear in the computation, because you're not determining the final momenta in terms of the
exactly.
So I guess that is the new, the universal result is really that, right? Assuming the asymptotic.
Yeah. What happens is that, like say, even for the leading or this 1 over u piece, you can determine this final momenta PA in terms of the initial momenta PA prime, like evaluating the trajectory using geodesic equation. But the corrections will be like, if you start this order, it will come at order g square. So order g term will vanish in that case, and it will start only contributing an order g square, and all order g contribution will be there. So only like this is exact at order g in a sense when both the initial and the final momentas are given.
Yes.
Yeah.
Thank
you.
And just one maybe if there's no other question, I can ask one more. I think Prahar's hand is still up, so I don't know if he has a.
Oh no, sorry, that was a
Oh,
mistake.
okay. So this is related to actually Gabriel's question. So I was a bit confused that the 1pi effective action that you used is the amputated 1pi effective action, right?
Right.
So why is it not the same as effectively working with the S matrix?
Yeah, I think that amputated Green's function.
Yeah.
Is it not same as the S matrix? Okay.
Yeah, this was my confusion also.
Amputated is fine, but
yes.
if one particle irreducible. Suppose I was thinking also about another example. Suppose I have a 3-to-3 scattering.
Okay.
In 3-to-3 scattering, you can have an intermediate particle, which is perfectly on shell. You exchange a particle. You have two 2-to-2 scatterings exchanging a particle which is perfectly on shell. Now, in that case, do you have to put to attach your graviton also to that guy, which is exchange and on shell?
Why the exchange particle is on shell? Like suppose 3 particles scattering is happening, P1, P2, P3 momenta. The exchange particle have momenta P1 plus P2 plus P3. So and then propagator is like 1 over P1 plus P2 plus P3 whole square plus M square, and say all the particles are identical. So this is not a on shell, right? This propagator.
Okay, you have say particle 1 and 2, which give 3 and 4. This particle 4, which is on shell, is hit by particle 5 and gives 6 and 7. Yeah, it's a well-known process which occurs. It cannot occur. But in general, my more general question is the following. The soft theorems, do they apply generically or always? Generically means for non-exceptional momenta. So suppose you have a 2-to-2 process and at t equals 0, and you exchange a particle which is on shell. Do the soft theorem apply equally well to this exceptional kinematical?
But I feel that since you have to conserve the momenta, like all the sum over the incoming and outgoing particles momenta plus soft graviton's momenta, and if you demand this thing, then can you really, the condition you are telling that the exchange particle is, or the intermediate particle is on shell, you can choose such a momentum configuration just consistent with the total momentum conserving delta function? This is not clear to me, possible or not.
Yeah, what I'm saying, for instance, in that 3-to-3 process, you can, since you fix the external momenta, you can fix in some way that 3 particles exchange with the other 3 particles an on-shell particle. That is perfectly allowed kinematically.
Okay.
So in that case, is the recipe of attaching external gravitons only to the external legs justified, or do you have to add extra diagrams? This is a little bit related to this question about one particle irreducible. And I thought at the beginning when you started with gamma, that you wanted to avoid those situations by talking about one particle irreducible vertices. Then you never encounter that situation. But if you talk about the full amplitude, that full amplitude can have intermediate states on shell. It doesn't happen in 2-to-2, but it happens in 3-to-3, 4-to-4, 4-to-5, I'm sure, and so on.
Okay, I have not thought, so I have to think, and maybe in the next discussion when Ashok Sen will be here.
Yeah, that's right.
Raise the point and
it's just a curiosity, I'm sure there is a simple answer to
Okay.
that.
Okay.
Yeah, but I think Byrne et al.'s proof, Biswajit, from gauge invariance applies generically, right? So at least that from that proof, we know the leading soft factor probably is true for any configuration of momenta. Right?
Yeah. Yeah.
From the gauge invariance argument.
Yeah. But I mean, you can view the subleading terms as being emissions from, part of it to be emission from internal legs, right?
Yes, yeah. that is certainly
the subleading.
Right.
For the leading ones, it should be like.
Yeah, it is only.
Yes, only from the.
Yeah, should be correct. So I was wondering if you start with effective action, one particle irreducible, you seem to get some extra diagrams when you put back together the gammas to make the full amplitude, but they must cancel out. Perhaps the reason is that in one blob the particle is outgoing, in the other blob the particle is incoming, and maybe there is a sign and that cancels. I don't know. I have to check.
Okay.
Maybe that's
okay. Okay, I'll think about it, and maybe in the next discussion.
Discussion tomorrow.
Gabriele, in this limit that you're talking about, don't you have to? Isn't there like again an order of limits question, like whether like how far unshell, like how far away from unshellness you are with this intermediate exchange state versus like how soft your graviton is? Like there is some virtuality Q. There's some virtuality Q squared, how far you're away from the pole of this intermediate exchange state.
Yes.
And then like depending on what omega is, like it like kicks you like completely unshell or not, right? So there's like
you are absolutely right in the case of 2 to 2.
No, I mean, I was looking at your 3 to I was looking at your 3 to 3 scattering because like
especially if as it says, you fix the kinematics, the initial and final momenta, you can make them such that you are exactly on shell.
Yeah. I agree. That's what.
So in that case, I don't know. In that case, but then if you are slightly off shell, then maybe you're right. Then it
No, but I think. Yeah, I don't know if these. Yeah, I don't know if these soft theorems are supposed to hold for extremely special kinematics.
Exactly.
I mean, you could also. I mean, I think you can even ask the same thing, like in more and more, like if you make certain legs more and more collinear to one another, go to special kinematics that way.
That too. Yeah. That's right. Some theories may apply to generic momenta where you exclude those situations. But in 2 to 2 scattering at high energy, for instance, in the work with Amati and Cefaloni, we found occasionally that depending on the omega, emission from the internal legs are also important. Well, we know they are important at finite omega. And as you say, if you are at small omega, then it's really a competition between how off-shell the guy you exchange is and how big is omega. There is some kind of competition between the two. And as you know very well, for the total energy emitted in gravitons, it's important, right, to keep the emission from the internal legs. The H diagram that you also computed gives a contribution to the total radiated energy.
I think if you go to special, like from a diagrammatic perspective, if you go to a special kinematic regions, you have more regions you have more like loop variable regions to consider in general.
Yeah,
right.
I guess you're right.
There's another, if you have another scale, like there is like this like particular scale that you now are introducing. So now you have to analyze your loop integrals more carefully, and like more scales can show up, not just the soft scale that you're usually considering for like fixed angle scattering of the hard particles.
Yeah, if you are not at fixed angle, look in the gravitational scattering problem, the momentum transfer is very small. right? Your T is very small. Your Q square is very small. Is actually H over B, right? H bar over B. So it's really, you know, quantum. So in that case, how important is the emission of soft graviton from the Coulombic graviton that you exchange?
From what I remember, I think the soft theorem derived from gauge invariant are valid for any momenta.
Yeah.
Provided that you have enough external particle. I mean, on the 4 point or on the 3 point, it's not easy. I mean, it's complicated to derive. But if you go to 5 point, then there is no problem. And on the problem of 3 in 3, if the original, if you are on top of the pole, you're on the top of the pole in both sides.
Yes.
Before, and so it doesn't matter, I think.
There is a cancellation, you mean?
Yeah.
You don't have to include an emission from the internal on-shell particle.
No, I don't think so.
Mm-hmm. Yeah, that's, I believe, also to be true. But okay, it's not obvious when you discuss things in terms of gamma, because when you discuss things in terms of gamma, in each gamma, you do have an emission from the particle you finally use to join the two blobs. You see what I mean?
I don't know if the question that one works with gamma,
yeah,
it's a problem to get, for instance, if you work with the amplitude, I mean, to derive a soft theorem for graviton or for dilaton, you do the same calculation.
Mm-hmm.
But probably from the effective action is not trivial.
Correct. Actually, in the subleading case, we did show that the contribution from the dilaton, I mean, when you look at the soft theorems in string amplitude at subleading order, I think that we could derive it even from the 1pi effective action in higher than 4 dimensions. So it matched with the result that were obtained.
Yeah, in fact, in the dilaton case, there seems to be complete universality at the subleading level. All the string theory have the same behavior, which is not true for graviton. I mean.
Yes. So we could get that from the 1pi effective action also.
I see.
We wish, yes.
So it must work somehow.
Yeah.
Yes.
Okay, any other questions?
One very last one. Can you go back a moment on this question that was asked, I think, by the chairman about the phase? I mean, whether all these logs come with a phase, come with an eye, come without an eye?
Okay, yeah. So I can show maybe the expression for the phase term.
Because you wrote phase and then you commented that finally only the real phase contributes, but I don't see it in.
Yeah, so here I have written down the waveform. This is basically the phase term which I was mentioning.
Okay.
So this is like order G and this is PB dot K. So omega log omega piece. There is also a log R piece, which basically gives the time delay effect. So that in omega going to 0 limit, we can forget for a moment, but that basically tells us that what is the cutoff. And so this is, so this is the classical phase piece. And what I am going to show that if we just evaluate this K phase piece with retarded Green's function, then only we get this term. And this actually matches with the classical explicit computation. But this phase piece, if we compute with a Feynman propagator, then this contains also a real piece, which I am going to show. So with this imaginary, there is a real piece also, but that does not contribute to gravitational waveform that appears in the soft factor. So this is, okay, so let me show. So this is the expression for the phase term. And the first part is, which I just shown, like contributes to the classical waveform as a phase, but there is another term which comes from the like in the, if you use Feynman propagator for the graviton, then this graviton has a like 1 over L square plus I epsilon, and in the contour deformation in the L0, if we contour deform L0, that piece actually gives extra contribution, and you can see this is this I and this I multiplies, and this is basically a real part.
I see. So both are present.
Both are present in the S matrix computation, but in the classical limit, the second part is not coming.
So which one I'm supposed to believe? I mean, is the quantum piece suppressed?
Yeah, quantum piece is suppressed. Like if you, like what happens is that if you consider the like energy of the gravitational radiation is small compared to the finite energy particles, which you can achieve in large impact parameter regime, then you can see that this piece, like if you write, is suppressed relative to this part.
Oh, it is. I see. It's not obvious, but it is.
Yeah, it's so it so we, like if we just write down the full soft factor, so I don't know, so in the this slide, so here I have written down, so this part actually the first two lines appear in the classical waveform, but not the last two lines. But in S matrix computation, in the soft computation, both all the terms are there. But if you take the momentum transfer is small, or the energy of the gravitational radiation is low, then you can see that first two terms are dominant relative to the last two terms.
Oh, okay. So this is goes with the long distance or yes, small momentum transfer limit.
Yeah, in the low momentum transfer limit. Yeah.
But Biswajit, they vanish only at leading order, right? I mean, there will be contribution.
Yeah, it's not exactly zero. So the point is that if you just substitute the final momentum of the particles is initial momenta plus some correction, and the correction you know in order of g. You can show that at leading order, when the correction is not present, these two lines are vanishing. And but like in like corrections, you can find out the correction, but the correction is more suppressed because when the momentum transfer, which is t, you are calling is small, this term is like suppressed in power of t.
But it's present in principle. It's present. I mean, it's present.
Yeah, in principle, in the soft, like in the soft factor, quantum soft factor expression, it is present.
Yeah, but so it boils down to the fact that the momentum transfer has an extra h bar.
Yeah, so like so somehow like when you derive
everything in terms of the impact parameter, then it's h bar over b. So
yeah,
maybe this explains why it is there only at the quantum.
No, but I mean, if you take the final momenta as initial momenta, but plus an impulse, so impulse is also classical. Then these terms are present when impulse is taken into account. So I think, right, Vishwa, is that correct?
Yeah, but what I'm telling, like it possibly, like if you take the impulse to be small, then at least
in leading order is zero, but the impulse is classical quantity. So if you include the impulse, then this term is not zero. It's not going as h bar. I mean, it's not a h bar vanishing.
But actually, Alok, like I don't know, like if you have a like particular expressions for the impulse, and if you substitute here and try to check all the orders, like whether it is really in higher order in small impulse or zero, non-zero, I don't know. I can like that possibly needed the particular form of the impulse to substitute here.
Yeah, right, that's true.
Only so the leading order I can say it is zero.
In the 2-2 scattering, you can show that if you go to leading order in impulse, there is a cancellation for 2-2 scattering.
Yeah.
But we don't know if it's zero.
Yeah, that is what you have done actually. Like, I think in your recent paper. Yeah.
Thank you.
Okay, any other questions? So Vishwajit, I have one final question, also for Enrico and Gabriel, maybe, that in the recent work in deriving classical quantities from the amplitudes, there is this method of regions technique which is employed, where you divide the loop momenta into potential and radiation and soft region.
Right.
But in the case of large impact parameter, the radiation region is where the exchange momenta is, as Gabriel was saying, of the order of impulse inverse, impact parameter inverse.
Exactly.
But the contribution you get for the tails is from the loop momenta, which is much larger than the frequency, radiation frequency.
Yeah, yeah. Like what I can tell in this S-matrix computation, the first two terms actually comes from the potential region. Like if in the language potential and radiation region, and the last two terms comes from the radiation region when you take L0 in order of L, where L is the momentum of the graviton.
But yeah, that was my doubt. That I thought you said L, the integration region is L much larger than omega, isn't it?
Right. L is much greater than omega, but omega is the external energy. What I am telling is when L0 is in order of L vector, which means you are taking the pole from the graviton propagator itself.
Okay,
which
thanks.
is known to be the radiation region.
I see.
Right.
So this is the radiation region contribution.
And this is the last two lines are the radiation region contribution, which is suppressed relative to the potential region contribution.
Okay,
where basically the massive particle poles contributes, propagators of the massive particles.
So that means the quantum piece is the radiation region contribution.
Exactly. So that's why we interpreted that as some radiation backreaction effect, though we don't have any like classical or other understanding like without this derivation.
So you expect in classical limit these terms to be not there. So you expect only the potential.
Since like we have given an independent classical derivation and we have seen these two terms are not appearing, that means in classical limit these two terms should not be there. But how to take from this quantum and classical without taking small momentum transfer, that is not clear.
Oh, thank you.
Yeah.
So let's thank Biswajit once again for an excellent talk.
Thank you.
And now Sasha or Gabriel can take over.